Okay, hi everyone. Today we'll be discussing the paper Deep Multi-Modal Explanation Model for Zero-Shot Learning. This was a paper that I studied for a couple of months ago to get an internship, and I don't this is the only paper that I've read in this domain. So let's see how well I can explain this. Uh, okay, from the title itself, we can see that it breaks down into multimodal. So which means we have usually it means that we have textual as well as image input output, and the model takes in the input from various modes, or it outputs various modes. And explanation model. So explainable AI is basically when we try when we have certain algorithms or methods for the neural network model to explain to us why a certain decision was made. For example, in the classification problem, it will uh, tell us which parts of the image that it was attending to, or give us a textual explanation of why a particular uh, why the classification decision was made. Coming to the third main part of the title, zero shot learning, we'll see into what zero shot learning is. So, from the title itself, we get to just what the paper is going to be about and what to expect from it. With the abstract, they give us a motivation for why zero shot learning is important, and what the paper, what the main contribution by this paper. So they explain that to perform a classification task for zero shot learning, uh, learning visual and semantic embeddings are very important. And at the same time, this paper focuses on explanation model. So at the same time, generating complementary explanations to justify the decision is unexplored, and hence this paper. Uh, so the contribution of this paper is they built a novel deep multimodal explanation model, which means that you have two you have image explanation for the decision as well as a textual explanation for the decision made. Uh, that this incorporates joint visual attribute embedding. We'll see what joint visual attribute embedding module is, and multi-channel explanation in an end-to-end fashion. So all the entire model from start to begin, we are not interfering the model at all, or we are not pushing anything. The model learns everything from input to output along with the explanations. Going ahead, okay, they are just summarizing the entire paper. What this is, they are saying that we have attribute activation maps, class activation maps. This won't really make sense right now. We'll see what it is when we get into the paper. And for the textual explanation, we have three LSTMs. They say. Uh, all right, we'll see. We'll see this more in detail inside. So, coming to zero shot learning. So, a very good example given the paper for zero shot learning classification, just zero shot learning is uh, for instance, we are able to recognize a picture of a panda by hearing the description black and white bears without ever having to see them. So, in zero shot learning, the problem statement is such that your model, your classification model, let's say we are dealing with classification problem. The classification model is trained on for certain classes, which are seen classes because the model has seen those images and those classes while training. But the model has to, while during inference, the model should be able to classify the unseen classes as well. So, if you how would that be possible if you're not training the model ever, or the model has never seen the image? So that the way we ask the model, the way that model describes what class it belongs to, we don't have a particular node that it can point towards, because it hasn't learned the mapping from the image to a particular class, because it's an unseen class. So the way that the model can tell us which class it belongs to is by generating a vector which describes which contains some semantic information about the class. So uh, if we have an image input in the model won't give us the third node or the third class is the uh, class that we are predicting, because it has it does during training it does not have the nodes to. So we'll see how this entire framework is there. So the model is expected to learn a vector for the unseen prediction, and hopefully that will give us more information about what it is trying to predict. So, given just the description that black and white bears, if you are given a photo of a panda, you'll be very easily able to recognize that this is a panda. So there is some common description where common textual description or understanding that you already have in your mind. You know what a bear looks like, and you haven't seen panda, but you have semantic information of what black and white is and how a bear looks like. So you can inculcate that, and then if you see a picture of panda, you are able to uh, find the similarity, say that okay, this might like I am very certain that this is the perfect app description for the particular image, even though you don't really know what particular class it belongs to. Just using the description, you are able to tell like the class label of the particular image. So in the core of zero shot learning, to learn a multimodal projection between visual and semantic features. Hence, we can't just have an image that is input to the model. We also need semantic features, which are usually textual descriptions. So you need textual descriptions which describes the particular image, so that you have a common space for your unseen classes, for the model to describe what class it thinks it is. Okay, we'll go ahead. If you guys don't get anything, please interrupt and let me know at any point of time. So they tell us what their motivations are. First primary question that they ask is, why do we need to generate visual and textual explanations for zero shot learning? We just saw what zero shot learning problem should be able to do. I understand that the entire like how we'll go about training the model, or like how it is done, we'll see it further, but we do realize what a zero shot learning paradigm is. So along that, like zero shot this paper is trying to create a model which is also explainable in nature. So they are asking the question, why do we need to generate visual and textual explanations for zero shot learning? So the success of zero shot learning is on the knowledge transfer. So all the scene data that it has accumulated, it needs to transfer that semantic knowledge for its inference in the future when it's seeing an image from a class that it hasn't seen before. So the success of zero shot learning is due to this knowledge transfer, like inculcating the knowledge from the previous classes, associating it with textual descriptions, which is a common area for seen as well as unseen classes, and then making and then during inference time giving a vector which will essentially be very close to what the unseen class vector should look like. Since the class labels of unseen classes are unable during training, that's why it's called zero shot learning. It is important to discover that semantic clues. Uh, it is discover what semantic clues the model has learned to maintain the knowledge transfer. Visual explanation in this paper, it's which region of the image is relevant, and textual description describes why a particular decision is being made in richer description. We'll see the examples. Okay, to just simplify, just a pipeline for this explanation model is this. So we have an image. The images that we see in this paper are from the CUB dataset, is Caltech USBC birds dataset. So that is you have like 200 different classes of birds, and for every bird you have annotations. You have human annotations for every single image, which is the uh, the human describes various attributes of the bird in the picture. So what's the wing color? As you can see on the right side, what's the wing color? If it's black, under part color is black, under tail color is black. What's the bill length? It's shorter than the head, upper tail. So you have these various textual descriptions about the input image, which helps the model to learn a common space for seen and unseen classes. We'll see how that goes. So let's just think that this is a input image and this is a text description of the particular image, and let's just say this entire block is a neural network which outputs a latent embedding. So this would be an image embedding that's outputted, and this is a texture embedding that is outputted. Using both these embeddings, we have three tasks at hand. So this is the image text passing through a neural network. We get a vector V. We have three tasks at hand. First is class. Second is visual explanation of why the particular class has been chosen. And third is textual explanation. We'll see more in detail how this is done. Uh, their contribution is they provide a deep multi-modal explanation model, as we saw above, and okay. So there are various questions on how do we formulate this problem statement, and how does the training go. Uh, we'll go ahead, and this is okay. This is a proposed model. Uh, okay, the problem setting. So what exactly? How do we actually set a zero shot learning problem, and how does the training go? How does the inference go? We'll learn all of that in more detail in this part. Okay, so problems setting, like this is very important for the rest of the paper description. So, or the methods, their proposed model description. So let me know if you don't understand anything. So, you have a data set. In a normal classification problem, you will have images and its labels. So let's say NS is number of labels. So in a training, in a normal classification problem, you'll have images and their labels. So let's say the number of labels are 10. So you will have your data set will consist of images alongside their labels from 0 to 9 or 1 to 10 in this scenario. Now the S stands for scene. So this is the data set of the scene classes. The model, the zero shot learning model, is trained on the scene class dataset only. It is not trained on unseen class, hence the word. And the inference is made on unseen class. We'll see it ahead. So the scene dataset consists of images or like a visual feature in this scenario. Visual feature is it could be like just a vector, like after passing the image, if you have a vector after you pass the image through image like pre-trained ImageNet model, say ResNet 101, then you'll have an embedding which is like a denser version of the image. So that's the like visual feature vector. It would be an image as well. And yi is the class label. Ns is the number of scene classes. Uh, so this is your scene dataset. Now going ahead, the test dataset is DU. DU is unseen. So it also consists of pairs, image, and label pairs. Uh, where your I goes from ns plus 1. So now whatever number of scene classes plus 1 till ns plus nu is like scene plus unseen. So let's say it was just 5 unseen classes. So it will go from 11 to 15. And ya belongs to yu. Yu is again the set for all the unseen classes. Which goes from S plus 1. So we have like 1 to 10, we have class labels for seen classes, and 11 to 15, we have class labels for unseen classes. Now, these are the two datasets that we deal with, seen dataset and unseen dataset. Now, the labels YS, seen classes, and unseen classes, their intersection is null. So there is no class which exists in the seen dataset and also in the unseen dataset. And all classes are described by user-defined semantic. So every single class, so to deal with how the model will like for unseen class classification during inference, let's say a zero-shot learning model has been trained. Now you show it an image of a let's say panda again, and it hasn't seen it before, but it has seen bear. Now it has to give us some outputs, some vector, which we can map to it. It can't give us a number like saying this is like 13th class because it hasn't been learned in that way, in that fashion. So it needs to output a vector which is similar, which gives us some semantic information about the class. So in this entire problem setting, all the seen classes as well as unseen classes, every single class, apart from just having images and labels, all the classes are described by user-defined semantic attributes. So for every single class, there is a vector. Like users have written semantic attributes for it, and there is a vector condensed out of those attributes of this textual or of the textual attributes. So like if you have a class, scene class where then there will be user defined attributes that the user labels it. So it will describe all the attributes of that particular class, and all those attributes will work like after passing through a network, you get a vector, and that vector will be representative of the class that the description is about. So every single class will have a vector, will have a class vector which contains the semantic information about that particular class. So now, like now during inference, the zero-shot learning model just has to output a vector, and then you can just match the similarity of that output vector with all the unseen class vectors, and any two like whichever is the closest similar, like the most similar vector in the unseen class vectors, that is the particular class that is describing. So in a way that the model in a way the model is trying to map the input images and the textual descriptions of a unseen class to a vector, which is very semantically similar to the class vector that is generated by the user. So in a way, it's learning. It's trying to interpret. It's mapping the semantic meaning of the images into that particular word embedding that should be similar. Will again see like what loss functions are being used and how exactly we get this vector. Now, these attributes, every class will have a vector that we said. So instead of having like class labels will be there, we won't have class labels for unseen classes. Like we are not training it, so we won't have labels. But instead, what we'll have vectors that define the properties of each and every class in the seen as well as unseen. That is denoted by A, which is the like attribute, and by I goes from 1 to s plus u. So every single class will have a vector attribute vector, which is called like which is denoted by capital A, which is the collection of all the attribute vectors. Given a test image, its class label is selected from YU, so unseen class label in the setting of zero shot learning. Okay, so this is just saying like during inference time, if uh, the input image is just from unseen classes, and it's a zero shot learning setting. But if the input image is from either unseen or seen classes, then it's a setting of generalized zero shot learning. Generalized zero shot learning is just saying that during inference, it should be able to predict with a good accuracy both seen and unseen classes. But in zero shot learning, it should just predict well the unseen classes that it has not seen before. Okay, so this is the problem setting of like how the data sets are there. So what we have here is just DS, seen class dataset, DU, unseen class dataset, and we have attribute feature for every single class. Joint visual attribute. Okay, we'll go to figure 2 and see what they're talking. Okay. We build a visual embedding model and attribute embedding model to co-embed visual and attribute features in the joint latent space.
Yeah, Sahil,
Yeah.
I have a doubt that when you can you go a bit, scroll a bit up? Yeah, when you here define that your unseen and seen labels intersection is null. So if your labels are vectors, then how do you define intersection or
So
union
in
in
this
a space?
yeah. So in this ys and yu are just like class labels 1 to like these are integer numbers 1 to s and like 1 to 10 and 11 to 15 in our scenario. We are just like every single integer is just mapped to a particular word. So one is dog, second is cat. So we are just saying logically that same class shouldn't belong in ys and yu. The attribute A is defined as attribute vector for every single class from 1 to s plus u.
Okay, so attribute is different from class label.
Yeah, class label is just one integer which represents which class it is. Just like in normal classification setting, attribute is for every class you'll have a vector which which is x dimension, and that will be representative semantically representative of the class.
So you input attributes and classes both.
We do have both classes. Like obviously, we when we have a data set, we know what class it belongs to, right?
Yeah,
And
I
we
got
have
it.
another vector which is a semantic representation of that particular class. Visual embedding. Okay. So what we like to get a embedding space like visual and attribute embedding. As we see here, we input the visual, we input the image here, and we get a latent embedding here. We input all the attributes here, and we get a latent embedding here. And after that, we, like this is a higher level pipeline. We get a class decision, classification decision, and the explanation models. Now we'll see how to actually get these latent models, like how to abstract it from the image and from the attributes itself, like because it's very difficult, like you have a image space, so like the vector space that this will be represented, it, it's in like in a higher dimensional space, it will be a different mapping than what you get from a textual description, because there is no way that we are like these are associated to each other. We as humans have a very good tendency to have this in the same vector space, and we can go back and forth very easily. If we see an image, we can describe it very easily. If we have a description, then we can visualize it very easily. But like no there is no restriction that we have put up while these models are learning, so as to like for them to have a back and forth semantic understanding, like mapping image to description or description to image and having that in the same data space. So we'll see how like just having like just passing this through a let's say ImageNet model and passing this through a like transformer and just having those final embeddings, the both of these embeddings will be in different latent spaces, and you won't really like you need to have them in the same latent space, or at least try to bring them in a similar same space, so as to like for the model to build the understanding of how to map the images to text and text to images for the zero shot learning purpose. So we'll see how that is modeled in this diagram. So this is the visual embedding module. Visual feature, again, this is a image, or in this paper, this is a vector. This is a vector with this is a vector from ResNet 101 after you pass the image. So this is basically a condensed form or like more rich form of the image. This is the visual feature, and this is the attribute feature. What attribute feature would be is basically the textual description that we have, as you see here. Wait, I think no, sorry. The attribute feature is the class attribute feature. Sorry. So whatever class the image we are looking at training right now. So visual feature will have the particular image. We know the images class for the like the corresponding attribute of that class. Will have a feature for that, like the matrix A that we saw earlier. One vector from that of the corresponding class would be A, and there is some distance feature. We'll see what that is. So basically, this attribute feature passes through some models, and we get a vector, and this passes. We'll see what like each of this is, and how this helps in our explanation model and zero shot learning problem. So joint visual attribute embedding, we build a visual embedding module and an attribute embedding module to co-embed visual and attribute features into a joint latent space. To ensure the discrimination of embedding features, we perform both category. Okay. So for you to get good representations of the image and the attribute, we'll go one by one from the first branch itself. Uh, we pass the visual feature through V through a neural network, multi-layer perceptron block, and we get a vector EV. Okay, so like forget the rest of the image, just look focus on the first branch. So what the first branch does is it again passes through a fully connected network, and we get a PCAT. What is a PCAT? PCAT is category level branch. So what this is trying to do, this is the visual feature. After passing through a couple of fully connected network, you have a final uh, final vector, which predicts what class it belongs to. So during training, you'll have the image as well as the class it belongs to. So in a supervised manner, you can train this branch. This is just a normal classification model, which is like which outputs a final softmax prediction on what class it thinks the image belongs to. By just training this single branch on in itself, uh, by pushing on for the like the softmax loss, like cross entropy loss, or for pushing like inversely pushing it for accuracy. The better the accuracy that you'll get here, or the lower the loss you'll get through this classification branch, the better like better representation of the like visual feature will be this latent embedding. So in a way, we are trying to get like more distilled and richer features built by this vector EV over here. This is the classification branch which you will train independent, like which you will train in order to make this in order to push this vector for a like much richer and better representation of the image that was inputted. The second, uh, so like very obviously, what would be the loss function for this branch? Anyone?
Softmax or something.
Yeah. So we'll have cross entropy loss, and the activation will be softmax loss, because we just have one class for every prediction. We'll have a softmax loss. So as you can see here, we'll have a softmax cross entropy loss for the visual embedding module. This EV which we get will have a softmax loss entropy loss over that. Now, this is just a category level branch. However, uh, the category level branch is not enough for us, because during inference we don't really have the like in this the number of nodes that we have as output would be equal to the number of seen classes that we have. But during unseen, like during inference or unseen classes, we can't really use this branch, because the unseen classes are not a part of the like seen class set as we saw before. So we can't really use this branch for inference purposes. So we need something else. So if we can't really assign a particular category to the image that's to an unseen image that we are getting as an input, what we do is we have a pipeline which outputs various attributes. So whatever image that we have, the model should be able to predict what like one should be able to describe the image. So it should be able to tell that uh, if it's a image of a bird which like of a class it has not seen before, it should be able to describe it like the beak is tall or like small, and it's black, but its feathers are yellow. It should be able to pinpoint what attributes it has. So it could be binary attributes as well, because we can't really have a continuous. We are not having a continuous attribute here. So we'll have binary attributes describing, let's say, just for feather, we'll have four different nodes saying yellow color, red color, blue color, white color. Then we'll have another four nodes saying like the beak length or beak color. So we'll have like n number of n number of attributes which describe the image. And in the CUB dataset, the images, all the images are handleable by the like by humans, and they have yes or no answers for all of these attribute questions. So while training, we can train the particular image and the attribute predictions. So a particular image will have this different attributes. So it will have a short beak. So it will be like second node would be a short beak attribute. Then seventh node would be a black feather attribute, and eighth node would be like blue eyes attribute. So we can train this independently in a supervised manner itself. So think of this as a attribute level branch. So as we'll have multiple predictions for this branch, what do you think will be the loss function for this? Like it's a 1 0 1 0 for like 1 0 prediction for each and every node, and we can have multiple predictions because multiple attributes will make up the image. What do you think will be the loss function for this?
Cross entropy again.
Yeah, but which one? Like what would be the activation function just before the?
Sigmoid.
Yeah, so we'll have a sigmoid cross entropy loss. This was the softmax for earlier. We'll have a sigmoid cross entropy loss for this attribute branch because it's a multi-level classification task. Okay, so this branch you can use for during your inference time also. Once it's learned how to map a particular image to different attributes, then what it can do is, even if it's an unseen class, it will be able to map that unseen class in a good way to describe that all of these features are there in this image. So
Uh, where is
this,
the
yeah,
where is the attribute features getting into this branch?
uh, attribute features getting into like the labels or the input.
The labels. I mean, attribute level branches is working with the label like attribute labels now.
Yeah, yeah.
So there is no input for that in this branch.
There is an input. The image itself, it's an input, and it's going three ways, right?
Yeah, but then
You just have to describe what attributes it sees in the image. Like forget everything else, just see at this. Like look, focus on this center branch, and it in itself is a model which is learning multi-class classification problem.
yeah, but where is it getting labels from?
Labels. That's what I said. Every single image, for example, in the CVP dataset, it has hand labeled like yes or no attributes, which humans have hand labeled it, and they mention like all the n attributes will be used as labels here. So we have annotations for it.
And this attribute block below is different from those attributes.
Yeah. This attribute is the vector representation for every single class. So whatever visual feature that you have, whatever image that you have inputted, and the class that the image belongs to, uh, every single class has a like shown here, right? Where was the matrix A? Was it? All the classes are described by user-defined semantic attributes denoted by A. So like there is a feature vector representation for every single class, which is the attribute A, and
Is this based upon the description?
in a way, yes. Like I don't really know the like how we are obtaining the class feature, like this attribute feature. Uh, I don't really think it was mentioned anywhere, but uh, like for now, there is just one attribute feature for every single class. Uh, that's generated in some way, but the description here is human description, that textual description that we get, not even textual description, it's a yes no question that people go through when after they like, during data generation we have like the workers see a image and then they answer yes or no questions about what attribute it has. So what is the color, yes or no, or like what is the length, yes or no questions. So those are the labels that are used here, and the attribute feature A here, sorry, and these attributes over here are done for every single image in the entire data set. The attribute feature here would be unique to a class. So every class just has one single attribute feature which describes in some way, in some semantic way, how like what is the semantic representation of that particular class. I don't really know how we generate this. Like I'm guessing in some way we have we describe like we accumulate the descriptions of various instances of a like images of a particular class, and in some way we compress it to get a vector. So it like it will consist of all like descriptions of. I'm sorry. Someone joined and started their mic. Uh, okay. So in some way, we have a we accumulate all the descriptions of all the instances in the class, and we have a compressed version of that which represents the particular class in some vector form. So I don't really know how this is obtained, but just for the sake of argument, we have a vector attribute vector for every single class, and the attributes over here are like labels and labels for every single image in the entire dataset.
Okay, so basically throughout the paper there are, when you refer to attributes, there are two of them. One is from the data set
One
and
is
the
a
other one is
class feature. Let's just say it's a class attribute vector, and the attributes here would be the different attributes of the image. Also, this is represented by small a because it's a vector of capital A matrix, and this is defined by a double t. We'll see when we go ahead. Okay, so this in itself is a multi-class classification problem. Okay, so this will help us in our zero-shot learning paradigm because uh, the like irrespective of if the model has seen that class or not, it will still be able to map that to various attributes, and those attributes can somehow be matched with the attribute feature. It's the same thing, by the way. Same thing as in these attributes will give us some semantic information about what the class should be, and that is also the work of this feature. It has semantic representation of that particular class. Okay, so like this, the first branch that we saw was category level branch, which is the classification branch. Second branch that we saw is attribute level branch, which is a multi-class classification. Now the third branch that we'll see, the entire purpose of this is to learn good feature embed. Like this latent embedding should be very good. That's why we are pushing in so many losses. We are also having classification problem, and it's back propagating through this. So it's improving this. We also have attribute level branch, which will make this embedding even richer and like generalized well. And we have another branch, third branch, which is called a reconstruction branch. So after passing this through a fully connected network, uh, this input vector v after passing through MLP block, we have EV. After passing through a fully connected network, we have V bar. So V bar, what we are trying to do is it should be as similar as V. So this is a like encoder decoder concept. Like MLP block, it's the encoder. It's mapping it to a lower dimensional vector, and after passing it through a fully connected network, it should reconstruct the input just so to push this embedding to not have any loss in information. So this in itself will ensure that there is no loss of information. Just because the input and output should be same, it has to be compressed in such a way that the loss in information is as minimal as possible while still compressing the information. So we'll get a rich like interpretation of the image as this latent embedding. So this is the reconstruction branch. So like, what do you think should be a like loss function for this branch? What we need is we need V and V bar to be as similar as possible.
Cosine similarity.
Yeah, that's the first thing that comes to mind. But anything else?
Siamese network. Sorry, that's a network.
It's okay. Anyone else? What do you think should be the loss function? We just want
Oh,
uh,
mean square error.
yeah, mean square error, because we really do want, literally want the vectors to be exactly the same best case scenario, even while having the dimensions to be smaller. So mean square error is the loss function that we use. So here mean square error is the loss function for the reconstruction loss. Now this was the visual embedding module. Entire thing, like entire process that we do just to obtain this latent embedding after passing the image. As you can see, visual feature here, the V vector is obtained after passing through a pre-trained CNN, in this case ResNet 101, and V passing through visual embedding model that we saw, it generates EV, and there are three different branches, and somehow we get the latent embedding. Now we'll see what's the attribute embedding part, attribute embedding module. Okay. So all of these losses, all the three losses are pushed so that we get a good and rich latent embedding, which we use for classification purpose and explanation purposes. Also, this was just empirical. They found out that after passing V bar, like after concatenating V bar with EV and then passing it through a fully connected network, it was able to perform better on the attribute level branch. That's why they did. There is no particular reason why they did. Also, it could be because the encoder uh, has some loss of information, and the fully connected network reconstruct this, and like V is passed directly. So this is like a residual block in some way, because V bar is essentially V in the best case scenario. So just a residual block which is passing so as to avoid information loss or to propagate the gradients. Okay, so all of these three losses are meant for, we don't use reconstruction branch for like inference purpose. Obviously, it is just for getting this richer. Category level branch is also for training purpose to get this rich. The branch that will be useful or like can be used during inference is the attribute level branch, because irrespective of the class, it gives us valuable information. Okay, now this was through the image that was inputted. Now to the attribute, A, uh, the A vector from this A matrix that we pass through. Uh, Again, a bunch of the neural network layers, and then we have embedding like EV. It will have a EAD embedding. You generate EA first, ED first, then you'll get a EAD, and then you have a loss over both of these. We'll see what that is. We did till mean squared error. Now attribute embedding. Now user defined attributes for each category. Each category means class. So user defined attributes for each class are quantized to be a real valued feature vector. So user have defined every class using text, and that is quantized to be a real valued feature vector A. Now what we do is, okay, interclass relevance. Okay, cool. Every single every individual feature vector A would be it contains attribute, every attribute feature of a class contains sufficient semantics to describe one independent class. But we need information much more than that. We don't just need rich vectors which describes every single class. We also need the interdependence of those class. Let's say our vector is defining a specific class of a bird, and another A1 is representing one class of bird, and A2 is representing another class of bird. Now A3 is there, which is describing attribute feature of a dog. Now birds are very similar semantically. Having just A1, A2, A3, we should be able to uh, we should be able to map that A1 and A2 are more similar than A1, A3 or A2, A3. But like we don't impose this anywhere. We just have textual descriptions, and we generate a feature vector A, which could be which is a quantized, which is user defined attribute quantized to be a real valued feature vector. So we need to impose this, that similar classes should have these feature vectors closer together, and dissimilar classes should have these feature vectors far apart. For this, we create a matrix. So this is called, it fails to capture interclass relevance. That is important, especially for unseen classes in zero-shot learning. So in zero-shot learning, again, similar to the panda example, it should be able to learn what attributes are similar, if the attribute, what attributes are similar to which classes and what attributes are dissimilar to other classes. So it should be, when it outputs a feature attribute vector for panda, it should be able to, if given a feature vector of bear, it should be able to give very high similarity because their semantic features are similar, but it should give high dissimilarity from all the other, like, let's say birds or snakes or reptiles. It should give a high dissimilarity in that way. So in that way, if you are pushing the model to learn that, we'll get valuable information we'll get valuable information. The model will learn valuable information so as to get good inference classification. So for that, what we have, let's just say we have like the attribute A matrix. We compute a distance matrix D, which is A transpose A. Now let's just say A matrix is composed of feature representations of all S plus U classes, right? So the dimension of A would be S plus U times X. Let's say every single class is defined by X X dimensional vector. So X times S plus U is the dimensions of A. Now when we multiply A transpose A, we'll have S plus U times X times X times S plus U. XS will get cancelled, and we'll have S plus U times S plus U. What this distance matrix is, every single row of this matrix, let's say 0th row of this distance matrix, will mention will have s plus u numbers, and for the 0th row of this matrix, all the rows will have a numerical value which is interpreted as a distance of the 0th class with respect to all the classes. So 0 comma 0 would be the distance of 0th class with respect to itself. 0 comma 1 would be the distance of 0th class with respect to first class, and so on till s plus u. Now this entire distance matrix D, every single row will have that class's distance from every other class, and this in a way is a semantic description or a vector which describes it apart from the attribute vector A. The even this information is important because it contains the interclass elements that we were talking about earlier, that it needs to know what classes are similar to this like what classes are similar to the input image and what classes are dissimilar to the input image. We need to know this. So for s plus u, uh, uh, like for s plus u classes, we create this distance matrix, and then we use this and then we use this vector in our embedding module. We'll see what how it is. So there's the input image here. You know the class of the image. This is everything during training. Okay, so you know the class of the image. Now the corresponding classes attribute feature. The capital matrix A that we saw, which is x dimensional, that corresponding classes attribute feature A is inputted here. Now that corresponding classes distance feature D. So in our s plus u times s plus u dimensional like D matrix, if it's the ith class, then the ith row would be the distance feature D, and that is inputted. So the corresponding attribute feature, which contains just textually compressed textual description, which is compressed in a numerical form, and distance feature, which contains information about what is the distance of that particular class with respect to all the other classes. So that is distance vector D. We pass this through again neural networks. We get a latent embedding EA, ED. We concatenate them together. We pass it through a neural network again, and then we get a final embedding EAD. Now, the visual latent embedding here, EV, and the attribute, the uh, uh, textual description embedding for that class, that particular class. This is class specific. Okay, so every single class will have only one attribute feature and only one distant feature. These are already computed. Visual feature would be whatever image passed through a resonant block will give you a feature, will give a vector that would be a visual feature. Now,
Distance feature is the matrix multiplication of A and A transpose, right?
uh, one row of the matrix multiplication of A and A transpose. A and A transpose multiplication will give you every single class's distance with every other class. Now,
Yeah,
yeah,
yeah. Like, is the implementation part of it?
sorry,
Like, how would you implement for a batch of for? Oh, okay, I understood.
sorry, yeah, it is class specific. So A matrix will be given because S plus U classes you already know, and distance vector is just multiplying A transpose times A. This will be there. Like you will have this information ready. You'll just uh, you'll just see what class this image is. Then you'll refer to the ith row for attribute feature and the ith row for the distance feature.
Yeah.
Okay, so this texture description feature, this distance feature vector, after passing through neural networks, it should learn a latent embedding, which is like if you see the textual description of any of the class, you will be able to map it to like you will be visually able to map. Also, similarly, if you have a visual representation, you should be able to map it textually. So what they are doing here is EV and EAD should share the same latent space, and they have another loss L center. What it does, we'll see.
This is done to have the attribute block and visual block in the same latent space.
Yes,
So that's the only purpose of this.
yes. So as A and D describe one semantic class from two different perspectives, we further concatenate EA and ED to get EAD. ASD algorithm will see the representation. We need to match EAD and attribute embedding EV by maximizing that compatibility in the latent space. So as you said before, as you mentioned before, that both of the vectors should be similar, not exactly the same. If they need to be exactly the same, we'll use the MSE. For reconstruction loss, we used MSE. But both of these vectors should be in the latent space, they should be similar to each other because they are providing different semantic information. You don't need them to be exactly the same. So in this case, what loss you will use is your cosine distance. So you want all these representations, this EAD representation and EV representation, as close as possible. That's why we have a L center loss, which is a cosine distance loss. So, like we want to know about the entire diagram here. Yeah, go ahead.
For the reconstruction branch, mean square is between the latent embedding and after
V,
the fully connected layer.
V and V bar, V and V bar,
What's V bar?
V and this V hat or V bar.
Yeah, so between this V bar and V, we find out mean square loss.
Yeah. And for in this L center loss, we have EV as input, EAD as input, and we need to have these latent embeddings to be as simple as possible. So we are using cosine less for this.
But if we are doing that, then what is stopping the fully connected layer to learn identity function?
Which one?
Like, like if we are trying to minimize mean square loss, right, in the reconstruction branch.
Yeah.
Now, to minimize this loss, why won't the neural network learn identity function?
It is very hard. If a neural network was able to learn identity function so easily, then resonant blocks wouldn't exist. You see, there is no resonant residual block here.
Oh, MLP block is resonant block.
It's not a resonant block. That's what I'm saying. It's like you'll see your MLP blocks is input, fully connected match norm, value dropout, fully connected match norm output. If neural networks are able to learn map or identity function so easily, resonance wouldn't have existed. That was my point.
Oh,
Yeah. The reason is why they don't learn identity function is because the uh, non-linearity is so complex that it is not able to learn, like it will have to learn the inverse of the entire non-linearity, that non-linear function that it passes through. So let's just say there is one sigmoid or like one ReLU here, so the model has to learn the inverse of ReLU after it passes through. So and you have multiple such layers, so whatever non-linearity it's introducing, the weights have to will have to learn the entire inverse of the function that the non-linear function is, and it's a very complex task for the model to learn. Also, another thing is like all the weights are zero centered, so uh, you won't have much deviation from zero. So if you are having your weights or your activations centered to zero, like, because we also have batch number, so it's doing the same thing. It's centering all the weights to zero. So when you have weights which are closer to zero, after you like whatever nonlinearity you're passing through, sigmoid of like f of x, you sorry, sigmoid of x you're doing, and if x is very close to zero, you are inducing a nonlinearity, or even in ReLU, you're inducing a nonlinearity in that scenario. But for you to learn the inverse function, like the model will have to learn the weights, which are like very complex, and we'll have to learn exact inverse of that problem. That's why we have f of x plus x, and the residual block will just like f of x can be very easily zero. F of x is like because the weights are zero, that term can be zero very easily, and x will propagate, and that is an identity function.
yeah. I just realized that there are other three losses also that will try to deviate it from.
No, even if the reconstruction branch is there, the entire problem, even like during like we have the encoder decoder model everywhere. Even in segmentation, we have encoder decoder model. Like the model doesn't just learn to map the image as it is.
Yeah,
That's why we have residual blocks. If you want to impose a like identity function behavior, then you'll impose residual connections. That's why if you have a deeper network, you use residual blocks because you need to impose identity function. In this case, you don't want to impose an identity function because it works counterclockwise. So hence there is no residual block here. Okay, so first branch, classification branch, like softmax cross entropy. Second branch is attribute level, sigmoid cross entropy. Reconstruction mean squared error between V and V bar, V hat, and another is center loss, which is just the cosine distance of EAD and EV, just to bring these interpretations as close as possible in the latent space. Okay. Now we have this model. We have the center loss. We are done with it. Now our final loss would be L embedding equal to alpha times L category, which is the classification, plus L attribute, which is the attribute sigmoid wala, plus beta times L reconstruction loss, plus L center. Now, this is a formula that they have devised for the final loss function that they optimize on. Okay. Now we'll go ahead and see what the values of alpha and beta are in some time. This is a multi-channel explanation model. We'll see what this. Okay. What do we do after like training this model? All these representations are good. Now we need, after we pass the visual feature, we need to generate the visual and textual descriptions or like explanations of why a particular classification was done. So that's what we'll see in multi-channel explanation module. Okay, so this is the essence. You know V was the input for the entire visual embedding module. EV is the first vector after we pass V through MLP block, and P attribute is the attribute like just before the attribute output. Okay, so why do we use these three? Okay, they're having a LSTM layer here just to create textual explanations of why a particular decision was made. Okay, from the input image. Now, why are they using just three V, EV, and P attribute? We need textual explanations during seen and unseen classes both, right? So going back here, we are using V, we are using EV, and we are using P attribute. Now, why are we not like? What are the other vectors that could be used for us to use during textual description? We could use P category. What's the problem of using P category as a means for generating textual descriptions? Anyone? Uh, Remember that we need textual explanations during seen as well as unseen. Hello? Hello? I'm not able to hear. Like, is my mic working?
Yeah.
Yeah. So why do you think, like any of you, why do you think we don't use PCAT as a representation?
PCAT as
Like for generating textual descriptions, we saw below right here, we use V, EV, and P attribute. So it is V, EV, and
because
P attribute.
PCAT doesn't have any information about the description of the scene.
No, it does, right? It's been trained. Description of the
Scene, like what things the image contains other than the category.
no,
Like
but like
I feel PCAT should be more like it should generalize better so that it is able to predict the category of class of the image better
yeah, but still
rather
it
than a
does.
general understanding of the scene.
Yeah, but it still has class. Like if you want a textual description about why a particular class was predicted, then it will have information about why the decision was finally made. The LCAT is the final decision that you're making, right?
Yeah.
So like to generate textual description, that would be a perfect scenario. But why are we not using pcat? Is again, as we said, like as I mentioned before, we need textual explanations while seen as well as unseen classes. When we are using an unseen class, pcat, this entire branch won't be used because this is just trained on seen classes. So this won't have any information about the unseen class. That's why you don't use pcat. Like, does that make sense?
Come again.
Uh, pcat is not used because we need textual descriptions during seen as well as unseen classes. Unseen the upper branch is not trained on unseen classes. It's just trained
Yeah,
on
right.
seen classes. So it won't give us any information. That's why we have the attribute level. Even when I started explaining this, this was like this is used during training, but you can't use this during inference because unseen class. This like LCAT does not have an output node for unseen class, but attribute level branch has uh, a common space where both seen and unseen classes can be described using attributes. Hence, we are using p attribute. Okay, why are we not using v hat? Uncle?
Yeah, because there is probably loss of information in that.
Yeah. Also, we are using v.
Yeah, B is there. Yeah.
Yeah. So if we are using v, we don't really need v hat if we are just optimizing to for it to be similar. And apart from the best case scenario, this would be a lesser interpretation of v. So another reason like we don't use v hat because we are already using v. Uh, so next, we are not using pcat. We got that. We are not using v hat. Why are we not using EA or ED or EAD?
It doesn't have visual information.
No, we are pushing it. We are pushing the latent embedding towards visual, right? So if this loss is small, then all of these vectors are good.
Yeah, but still, this won't contain visual information for unseen classes, huh?
No, but we are. This will have a textual description, right? We have a common semantic space where the representation of the image is there or the representation of the class is there. So what we need to for the model is to why you have made a particular classification when describing it textually. It could use information from these also, right? Because it is like this is valuable information about the class. This is valuable information about the distance of the class from everything else. So in a way, it will have the reasons why the particular image is of a particular class. Again, think about when we are generating a textual explanation. We are generating a textual explanation during training as well. Of course, you can just check how the model is doing, but during inference,
Wait, how do you have attributes for unseen classes?
you don't exactly.
Yeah, so that's why you can't use this because it does not have
Yeah,
unseen
exactly.
classes. Yeah.
Yeah. So the attribute features because you beforehand you don't know what unseen classes are going to be there, or you don't know the class label itself. You just have an image. You don't know what class it belongs to for it to map from the. Even if you have a matrix which has the class attributes, you can't map which row or which vector, which class vector you want. You have to choose here because you are predicting the class while the inference. So when it's a unseen, you just have an image. Even though if you have an attribute feature representing it, you can't use it because you don't know which exact like which class it is because you are like you're you can find out the most similar. They have mentioned that you can somehow find out the most similar attribute, but then it's just noise because it could be wrong and the accuracies are not that great. But yeah, the main point is you don't know what class the unseen class is, hence you don't have the attribute features and the distance. So you don't have this entire thing for generating text descriptions during inference, the textual explanations. Hence, we are just left with uh, P at V and EV. We use these three to generate texture explanations about why a particular classification was made. So this is the LSTM model. We input the word at time t. Description. Sorry. Uh, so uh, in this explanation text explanation module, you use these three vectors from earlier, and you have a word at time t, xt. So for xt equal to 0, you can just have a start word, like start token, that will be inputted. This is word embedding, so you can have any mapping of word embedding. You can have word embeddings if you want, or any other embeddings that you have. This is just a word embedding. Feature, you concat them. EV, you concat it. PAT, you concat it. You pass it through three different LS teams. You have those hidden representations. This is like LSTM visual, LSTM latent, because this is latent embedding, and LSTM attribute, because attribute prediction for the multi-class classification attribute. So you have these three hidden vectors, and you concatenate these, pass it through fully connected networks, and then you have an exp loss, which is like the objective for generating sentence level explanation is to minimize the following loss. This is this refers to log of p, so the probability of xi t plus 1. So at timestamp t plus 1, what word is it's predicting, given all the words from 0 timestamp to t timestamp, and the visual vector b, the hidden embedding ev, and the attribute embedding pat. So it's just minimizing this loss to get the textual description of why textual explanation of why a particular class was selected or predicted. Sorry. I think we should look at some images now. This is done. Yeah, so this is just a visualization, TSNE visualization of like they compress the dimensions from 512 or 1024 something to just two dimensions using TSNE, and you can see EA, ED, and EAD of this branch. So this EA, ED, and EAD of this branch represented here. You can see there are structural similarities between EA, ED, EAD, but they are visually like in the latent space, they are in different orientations, which gives us an idea that uh, they are able to learn, they are able to map semantic meanings from different perspectives. So EA has a different perspective about the like semantic feature that it's recognizing. ED has a different perspective because we have different perspective there. The attribute feature here is directly class dependent. Distance feature here is inter-class distances. These are different perspectives, and after you combine this and put it through a frequented network, you get a completely different perspective, and those have structural similarities, which mean that it is learning to map the same semantic meaning to a better embedding space. So this diagram describes that. And this was the loss that we saw. Okay. Uh, Now this model, we get textual explanations about a classification decision. Now they have done a study.
I have another doubt.
Yeah,
The output of this model is basically a vector.
yeah,
So then you put this vector in some language model to generate the sentence, right?
yeah.
Okay. So how does that language model understand this vector?
Uh, Understand this vector.
No, not that vector. Yeah, LTXP, the final one after fully
LEX.
connected layer.
Yeah, yeah.
This is a vector, right? This is not a sentence.
This is just next sentence, next word prediction, right?
Okay, fine.
So
So
this just has a distribution over the entire vocabulary, and it's predicting one word at a time, given x of t.
wait, x of t. What is x of t?
X of t is the word input at the tth time step.
Oh, okay, fine, fine.
You pass it through LSTM, concat this, and you have a distribution over the entire vocabulary of which word is next.
Yeah. So you can say that this whole thing is like an LSTM
Yeah,
unit.
yeah.
Fine.
Then they go ahead and analyze if we do require, like we did an analysis of why these three vectors were chosen. Now they go ahead and analyze if all the three vectors are required for the textual description that they are providing. So the image here you can see uh, it's a comparison of hidden features learned from three LSTMs. Okay. So 0 to 14, these are the words, and this represents what word the particular LSTM was focusing on. So this heat map says this LSTM, this LSTM, and this LSTM, what words it was focusing towards while activating to generate the next word. So as you can see, V and EV are particularly similar at most points, but like they differ in the end. So they are learning to look at different places. They are not learning the exact same thing. So it is like useful for us that it's able to look at different places. But the reason that they are very similar, I feel, is because V and EV just have a MLP block separating them, right? V and EV are quite similar, but P attribute goes through a lot after that, and it's specific to attribute level branch. So it's learning like the representation here is quite different than V and EV because it's just separated by MLP block. But it's not exactly the similar, exactly the same. You have some differences here, which means that both of these have some input for generating the next for generating the textual explanation. And P attribute is completely different to where it focuses on which part of the image it focuses on to generate the next word. So like this justifies why they are using all the three LSTMs. We'll also see ablation studies ahead, which will give what accuracy, like how good we get if you're not using one or two. Multimodal explanation generation. This is the text explanation generation. Okay, we'll see how image explanations are generated. And especially okay, we saw how we generate textual explanations. Now to generate visual explanations, we use a concept called class activation maps. So in the P classification branch, the first branch, you have a prediction over a particular class, and you can upsample the activations from that last layer, and you get a activation map which describes which part of the image the model was focusing towards or attaining to for a particular class representation. But we can't have class activation map explanations during unseen classes. Hence, we use something else called as attribute activation maps. What activation maps is all the different attributes that were predicted in the attribute branch, which is the center branch. You use the activation maps of all the attributes, and you'll get. Wait, this is not the figure. Yeah. So these are the attribute activation maps in this figure. So if the attribute activation map is just outputting three different attributes, then you for seen as well as unseen classes, you'll be able to get these attribute activation maps. And after you just combine them normally, you'll get a class activation map of like what all attributes it was focusing on. You can see an attribute activation map. So forehead color, then it's focusing toward the forehead. Belly color, it's focusing here. Throat color, it's focusing more towards the throat. So it's very impressive that the model is able to do that. And after you combine them, you have the entire class. Like combining all the attributes give you the class where it was looking at. So we have these attribute activation maps, which gives a visual information that the model is learning and uh, learning well, and it's looking at the right parts of the image, a lot of times the model tends to learn the surroundings of the image. So if you have a particular animal which like is on trees a lot, so it will learn the surrounding of the animal and not the features itself to discriminate. So if there is a animal which is more to like more found in ocean, so the images would be near sea and the like background will be blue in color. So the model will learn the environment and not the actual features of the class like, of the particular animal. Hence, these attribute activation maps and class activation maps help us to see if the model is learning the right things and it's not uh, bypassing the entire thing and learning wrong things to get correct answers. So this is just a visual explanation model of how it's done. We saw the textual explanation model. This is the visual explanation model. Okay. Uh, where did you guys last year?
Yes.
Where did you guys last hear me? I think I had disconnected.
Yeah, it was like for 10-20 seconds only.
Okay. So yeah. So we saw how textual explanations are generated through the LSTMs that we saw, and we see why all of the three LSTMs are necessary and all the vectors are necessary through this diagram. And we saw how visual explanations are generated through attribute activation maps. We use GradCam algorithm for this, and we combine the attribute activation maps to generate the final class activation map. And next we'll see is the explanatory consistency. So there are two things that we observe here. We'll see in figure 6, which gives us an assurance that the model is able to learn like learn in a good direction. So we'll see what that is. So explanatory consistency is given uh, similar instances like this class like both the classes are similar in this and they are uh, this is also same like the stance is same, they're doing the same direction and size and all everything is same in this scenario. And even in this case both the images are pretty similar, though they are different birds but they are of the same species and they look similar. So explanatory consistency is when they are generating these textual explanations, the explanation, textual explanation of this and textual explanation of this should be very similar. So you can read here, because this bird has a white belly and breast, blue wings and crown. The class is blue jay. Similarly, because the bird has white belly, blue wings, here blue wings is there, blue crown is mentioned here, your crown is there. So like they have similar textual explanations for different birds, but of visually similar. Even here, you have the same thing. This is for the seen classes. This is for the unseen class. Even in the unseen class, you get black crown, pointy bill. You get similar textual description. This is explanatory consistency, which gives us a sanity check that our model is learning good and the textual explanations are helping us. Uh, Now, moving towards explanatory diversity. So what we want is if uh, the image is captured from different angles and poses, the model should not the model should not predict that it's a different class, or the description should not change drastically, but it should also inculcate that the differences in the image. So it should be able to mention what difference is there between this and this image and still predict that the class is same. So in the first image, it's because the bird has blue crown, white belly and blue head. uh, okay, so in this it was not able to see its beak, but in this it is able to see its beak, so it's making the conclusion after seeing its beak, because it's like the background is very easy to identify the beak from, so it's using beak as a textual description, a textual explanation of why it's creating this as blue jay. And even in this, whatever parts or whatever attributes there are available in the image, it's describing that in the textual explanation and predicting the same class. So even in this case it's like very occluded, and still it's able to predict on same class as yellow-headed blackbird. And textual explanations uh, describe us why it's making that class prediction. So having explanatory consistency and explanatory diversity both at the same time gives us a sanity check that our model is doing well, and uh, that is like this is a metric that we can we don't really have a hard metric for it, but this is a way that we can quantify how good a model is. So that was it. Now we'll see training procedure. Won't go too much in depth in this. So uh, training procedure is they try training, joint and separate training. So what is joint? Yeah. So now what you could do is you're training this and this. You could train it jointly, or you could train it separately. That first you train this, then you train this, and then you have a loss over. Sorry, first you train this, then you train this over this loss and all the three losses, something like that. So there are two. Uh, the optimization objective of the model is to minimize both L embedding and LEXP in the multi-channel explanation module. Uh, LEXP explanation module is the loss function that we saw in the end here. So, no, I'm sorry. L embedding is this one. Okay, okay. Sorry, I made a mistake while justifying what separate and joint training is. So, L embedding is this loss, which is the like addition of all these losses, and L explanation is the explanation loss of the LSTM model textual explanations. We don't have any loss for visual. We'll see why not in the end, and we'll see how how we could have a loss for visual explanation as well. So the optimization objective is to minimize both L embedding in the visual attribute embedding module and LEXP is the explanation module. So we pre-train the embedding module at first, so as to get good, at least some good representations. And after getting good representation, then we can pass it through LSTM to start training our language model. Note that L explanation will also affect the optimization of the parameters in the embedding module. We call this training strategy is joint. In addition, we also evaluate another strategy, namely separate training. Likewise, we'll see what that is. Uh, what they are saying is, if we train these together, if we L embedding and L explanation, we could joint training is we train L embedding and then we freeze this. Sorry, we don't freeze this. That would be separate training. Separate training would be you train the embedding model completely, you freeze this all the weights, and then you just train the explanation module. That would be a separate training. Second thing you could do is you could train L embedding and L explanation together, but just because L explanation diverges quicker, so what we do is first we train embedding loss first, just like as a pre-training method, and then we train both L embedding and LEXP together, so as to get like back propagation from this, and we can have better uh, representations of visual and latent and attribute prediction representations. So they do both joint and separate training. What they find out is joint training gives you a better model, but separate training is much more faster. It's 1.5 times more faster. So if it takes like 50 minutes for separate training, it will take 75 minutes for joint training. But at the end of the day, they suggest that we do use joint training because that was the entire point, that the explanation module does not just give us more information about why a prediction was made, it also helps the embedding module or the entire module that is making the classification problem. The explanation itself helps these embeddings to be learned better during testing. Yeah, the hypothesis of zero shot learning is unseen classes should share the same semantic / attribute space with seen classes. So in the attribute branch, if you don't have attributes of the unseen class, so like if it's drastically different and you can't describe that class in those attributes that are given, then that won't work. You won't be able to predict what class that is because it's completely different from uh, the attribute space that it was trained on. So you need to have a similar semantic or attribute space, uh, like which again goes back with the example of the uh, a panda and bear one, that you need some similarity for you to understand what the new class is about. If you don't have any information about what I'm describing you, then you won't be able to visualize it. Meanwhile, attribute embedding per class is captured from the. It's okay. This is okay. So that's the testing procedure. They're just saying that a hypothesis is they should have same semantics as attribute space that we have in the second branch. Network details. They use ResNet 101, as I said before, and they do not fine tune this ResNet block on the particular dataset. So if you are using CUB dataset, you could fine tune this, but they are just using ImageNet uh, this weights. They have shown that you get quite a significant boost in accuracy after you fine tune the model, this ResNet model, on the particular dataset, but they are not doing it. Then the continuous attributes in the dataset act as the input attribute feature A. So in the dataset, it's fine. They have just mentioned that every class would have a attribute feature A. Binary attributes. Again, the binary attributes that we have are ground truth labels for the middle branch, and other details of the network. Now experiments. This is the interesting part. What they did was, for datasets, they used 3 different datasets to experiment this one. First is CUB dataset, 200 categories. So this is the birds dataset. AWA, animal with I don't remember. So animal with attributes, I think. Dataset which has 50 animal categories, and scene understanding dataset which has scenes, 717 different scenes, which it has to classify what type of scene it is, landscape or cityscape, that sort of thing. So they tried on all the 3 datasets. The problem with AWA and SUN dataset is that they don't have textual descriptions. Like they don't have sentence descriptions of the image. They do have textual descriptions because they have given, like, the binary descriptions are there. The binary contains for the middle this CUB dataset, apart from the attributes, the binary attributes that we train on, it also has, there was another paper released on CUB dataset where people have described the class, people have described each and every image through a description, through a textual description. So that could be used to see how well your textual explanation model is doing. But you don't have that in AWA and SUN, so they don't have that analysis in these 2 datasets. But textual explanation comparison is done in the CUB dataset. They just told us some about overlaps. Sentence descriptions for the images in CUB are there. Okay, evaluation metrics. Zero shot learning, average top 1 accuracy, which is T, is used, top 1 accuracy T, unseen class accuracy U, seen class accuracy S, and the harmonic mean of seen and unseen is calculated. For textual explanations, they use 4 different metrics: Liu for Meteor, Rug L, and Cider. And third, they don't. They explain that they don't have any ground truth visual explanation, so they don't have any metric to see how good your visual explanation is. But they suggest that you could use intersection over union. So after you get the class activation map, you could fit a box around the class activation map, and these datasets have bounding boxes for image object detection purpose. So you can have some intersection over union and get how good your class activation maps really are. But that again depends on other features, so they haven't used it. Training parameters, they use PyTorch to implement this, and they just told number of epochs. Okay, so zero shot learning classification ablation studies, we'll see table 2. So they used different strategies. First, they did not use D. They just used the category and attribute level. Then category attribute with center. Then center loss, category attribute. Like they are just trying out what if we remove one loss from the entire equation and see how that is working. And what they found out was also the type of training separator join. What they found out was model 5 joint training with all the losses gives us the best accuracy. 61.4 is the best. 32.5 is the best. 64.3 is not very good. So scene class, it takes a hit in scene classes, but unseen classes it gets the like the best accuracy. So like our main motive was that, and the harmonic mean is also the highest. So it kind of balances out. So they justify that each and every single loss function was useful, and joint training is better than separate training. That's the ablation study that they did here, and comparison with other methods. This paper compared to other methods. So when you come for zero shot learning, you get two types of papers. One is non-generative group, other is generative group. This entire structure is a non-generative group, but you also have generative group models which deal with zero shot learning. Now we'll see in table 3 how it performs with respect to other models. So in this, you have these non-generative models. These are generative models. DME scores the best. The top one accuracy best. Unseen accuracy is the best. Seen accuracy takes a hit, and harmonic mean is also the best. This is for the CUB dataset. Similarly for AWA2 and SE1 dataset. What they mentioned, the main takeaway from this is that in generative models, top one accuracy is low, but there are also the scene accuracies 59 or 53, 59, 57. You can see that it's lower than scene accuracies in the non-generative models. But the main takeaway is that unseen accuracy is very good as compared 47.9, 31.2. It's their unseen accuracy is very good. So they have generative models trade the S accuracy, scene accuracy for raising the unseen accuracy. That's a trade-off that generative models make. And in harmonic mean also, they get very good scores because their unseen accuracy is better than the seen accuracy of these. So that's the main takeaway, that generative models have a good like harmonic and unseen accuracy, but still the balance between seen and unseen is a like domain that we have to research on, and how to balance it and how to get even better results. So that was comparison with other models. That is the takeaway. Explanation, again, visual explanation, you could use intersection over union. Why? So how would you do intersection over union? We will define a threshold to binarize the CAMA. So class activation maps will define a threshold to binarize the map, and crop a minimal rectangle fitted around the salient region in the binary map. Now the problem with this is our accuracy, IOU accuracy will be determined the threshold that we binarize the CAM with, and we'll see the Ablation study that did with that. Figure 8. Figure 8. So impact. So having 0.2 threshold till 0.8 threshold, uh, higher the threshold, which means what does it mean? Okay, give me a second. Uh, yeah. Uh, so wait. What was I explaining?
After Ablation study.
Oh, this one. Sorry. Yeah. So we see, okay, point two and point eight we have to see. Uh, when the threshold increases from 0.2 to 0.4, performance is stable. Uh, we fix the threshold to zero point 0.4 for all image instances. Uh, as it is, I think yeah, here. A low threshold provides plasticity to detect the entire object, but a high threshold will, so like low threshold, it will give us, uh, it is expected to get a higher IOU because it will detect like it will give us the class attribution map of the entire image that it can, but higher threshold will just lower the amount of activation map that is present. So they got a soft spot at zero point 0.4 threshold and they use that. And for textual explanations, they yeah, they try all the different explanation methods, or just the visual, like singular explanation methods, and all the three together, and the different training strategies separate and joint. They found out that the LSTM joint explanation gave us good, uh, textual explanation metrics. Okay, so this can be done only in CUB dataset. In CUB dataset, every single image has a sentence description uh, by the like by the worker who is annotating. So apart from the binary attributes that they have labeled, CUB also have textual descriptions of every image. So the textual explanation generated by the model and the textual description from the worker itself for that particular image is used for generating these benchmarks. So Blue for Meteor, Rook, and Cider, all these uh, we get through all these metrics we get through comparing both of those. And IOU, you can see ground truth bounding box is green, and the red one is our class activation maps bounding boxes. So expression is there. Side games. Additional analysis, the okay, we'll just see the diagrams directly. So in this, this is qualitative results for classifying unseen classes. First two instances are success and the last two are failure. So these are the success unseen classes and these are the failures. So they see, you can see attribute activation maps and games. They're pretty good. Uh, this is the like the ground truth and predicted cards are same in the correct predictions, but in wrong predictions, what happens is they predicted wrong classes, but the class that they predicted, we could see it's visually very similar. This and this is very visually similar, and this is visually very similar. So they are trying to explain that even if our if in unseen classes we are not exactly able to give you the correct class prediction, the class that we are predicting is quite visually similar to the input unseen class. And the ground truth statement and the generator statement both will have similar textual description. Like it has uh, yellow nape wings and white sides. This has white belly, breast, and short pointy bill. It has a small black beak. So, like the textual and visual explanations would be pretty similar, but still, because both of the classes were same, it did not get the correct prediction class. And in this, okay, in this SUN dataset, they just see the class activation map and compare it. If it's like the model is learning good. So the highlighted thing, the dot track in the last row, this one. So apart from the motorcycle, the entire like it has to it has to detect the scene dirt track. So all the attribute activation maps combined together will give a class activation map. All of it is focusing towards the regions which is the dirt track apart from the motorcycle. So it's conveniently conveniently ignoring the motorcycle and uh, giving its attention to the background itself, which is a very good uh, showcase of the model's abilities. And okay, so apart from training loss and test accuracy, we'll see that here. We see that while training, all the training losses go down. So that's a sanity check for them, and the accuracies go up. And here is the alpha. We'll see that in text first. So training loss and test accuracy we saw. Classification loss has a higher decrease, larger decrease than others. Just because classification is a well-defined problem, it's way easier. Analysis of lots weights. So the alpha and beta, they were empirically searched from ranges 0.1 to 5 and 0.1 to 10. They did a grid search over this, and what they found out was here. Alpha when set to 1 gives us the best accuracy. Alpha when set to 1 gives us the best accuracy in all the three data sets. And beta when set to 1 gives us the best accuracy. So if you don't remember what alpha and beta were, we'll go back. This is alpha and beta, and like the category loss, attribute loss, then the reconstruction loss, center loss. They've empirically found out that alpha and beta, when set to 1, will give you the best result. So basically, they're just adding all the terms here. But like that's a good thing that they did do research and found that out. But like there was no need of alpha and beta, it seems. Uh, question was done. This is done. So when alpha is set to 1, and there's a large boost, and when beta set to 1, there's a large boost. Reproducibility, they which figure number? Figure number 15. So they just ran the same models, the best model that they have, 5 times, and they saw that they got exact same accuracy and exact same accuracy, T, U, S, and H accuracy graphs, which means that it wasn't the model is not sensitive to initializations of weights, and these are pretty solid predictions, and you will get similar benchmarks. So you can easily reproduce the results. That's the main underlying thing that they are trying to say here. And illustrator visual embeddings, we did visualize it. 13. So this is just unseen classes. Then unseen classes, TSNE 2-dimensional, we are able to visualize them. TUB, AWA2, Sun, they are like pretty good at differentiating all the classes and multiple objects in one image. Figure 16. Even this is impressive. If you have multiple classes, your model is still able to pay attention to both the instances of the word, and your final class activation map looks like this. So they just see that it's not even though it's trained on just one instances of words, it's able to actually learn what like even if it's two of them are present in different parts of the same image, it's still able to attend to them, which means that it's actually learning the features and not just the position in the image that the objects are generally there. And that was the fifth tabulation study. Embedding methods on sentence. This was the study that we saw, model 1 to 5. Model 5 is basic they're having different losses. They compared which model would be better. Tables. Model 1 to 5 and separate and joint training. So having all the losses together and having a joint training gives the best metrics here. Explanation methods. In just model 1, if you do joint, you'll get better results. If in model 5, you'll get joint better results, and model 5 is not better than model 1 metrics. From unseen classes to unknown classes, they also tried to have unknown classes. So they don't have corresponding attribute features that are predefined in the dataset. Figure 17 we'll see. So these are unknown classes. They mentioned that they don't have similar attributes. The attributes that are defined in the dataset, they can't be labeled I don't see how, but they mentioned that if you even if you don't have attributes which are similar, the vector that you get, and if you compare that vector with the attribute vectors of every class, and you choose the top four similar classes, you get similar looking images, even if this particular bird does not have a similar attribute uh, space as the other birds. Like that's one question. Like how would we, in contrast to conventional ZSL, we explore a challenging yet practical scenario, test classes and no corresponding attributes. I don't know how they don't have similar attribute features as the predefined data set. So they just extract visual embedding and compare it with the attribute embeddings of the existing training classes, and they choose the top four and they show it here. Conclusion is they just explain, they provide a model which has explanatory consistency and explanatory diversity that we saw. The classification is competitive, as we saw, with at least non-generative models. Generative models do perform better, but in non-generative models, this their classification performs the best in almost all the metrics. And limitations are we can't train visual annotations. You'll need a object detection type model for training visual
When
explanations as well.
when there is an image with a dissimilar attribute vector, then your visual vector will still be in the same latent space now.
Can you
So
give
it
me an
should be
example?
able to predict. Like go to that bird images. Yeah, so over here, if you enter the first bird image, which is an unknown class.
Uh, Unseen class is different, unknown class is different. I'm thinking that this can be described by its wing color, belly color, and its beak, which are the attributes which
Yeah.
are there in this. That's what I was thinking. Why they are saying that these attributes are not there? Why is it an unknown class and not an unseen class? That's what I'm thinking.
From what I understood, attributes are basically the human labeled attributes pass through some
Yeah, yeah.
network that generates a vector.
Okay, so you're saying,
A vector or something that generates a vector basically.
yeah, yeah. Okay, so they're talking about that attribute. Wait, has no
Yeah,
corresponding
because
attribute
when you go
features.
to the attributes, like we were talking about two attributes now. One was the
Oh,
labeled ones, and
right. They say that this is not there in the S plus U matrix.
yeah, yeah.
Okay. So what they are doing is they just they extract the visual embedding and then compare the similarity with of the visual embedding V or EV with respect to all the attribute features which are there in S plus U matrix. Okay, got it.
Yeah, I mean, if you like when you train your like when you are bringing all the visual and attribute visual vector and attribute vector to the same latent space, right?
Yeah,
So for so I think at some point having attributes becomes redundant because even if you have an image, you would end up in the same latent space when you pass it through your network.
no, I didn't understand your point. Sorry.
Uh, See when you go when you
Explain.
have some attributes for an image.
Yes, right.
Yeah, so when you have some attributes for the image, you generate an attribute embedding, which is
Mhm.
in some latent space, right?
Yeah, yeah,
Now, this latent space is shared by visual embedding module too.
yeah, yeah.
So, in case of absence of attributes, and if you have an image for that, the embedding of your image would end up in the same latent space as your attributes.
Yeah, yeah.
So even if attributes are non-existent, you can just rely on visual embedding to classify
Yeah.
or
Understood.
generate an explanation.
Understood. So the attribute feature here and distance feature here is has like S plus U dimensional matrices. So the
Yeah,
uh, the U part of it, those are the unseen images. So when we pass a unseen image through this, we'll get a latent embedding, and then when we compare this latent embedding to the attribute features here, then we should get the unseen class attribute feature similarity as the most. But
Yeah,
unknown class would be it is not there in S plus U set. It is different from that. So even if you don't have your class in S plus U set, and you still compare the similarity of EV with A, you still get top four predictions will be visually very similar to what your unknown class is.
correct. Because one of the goals of the model is to make visual and attribute embedding similar.
Understood, understood. Yeah, that's why it's able to predict the unseen classes as well because it generates EV, which is similar to the A of the corresponding class, and it's able to identify which class it belongs to.
Yeah.
Makes sense, makes sense. I think we're at the end. Yeah, so conclusion discussions they conclude explanatory consistency and explanatory diversity is there. They have competitive classification results. Limitations is we can't train visual explanations. We need like CUB has bounding boxes, but it's not really for like activation maps. So we don't have ground truth for activation maps. So then again, the thresholding and like all of those things come in. So there is still some work to be done to have some ground truth for these annotations. Uh, exactly that they said that CUB has bounding box, so those could be used, but then the thresholding thing comes in, and language modeling could be better. Bidirectional and self attention mechanisms could be used, uh, and I've evaluated the modules. And these metrics are not proposed for explanatory models. Yeah. Future work again incorporate grammar models just to get the language model even better and explanation model better. So I think that ties everything together. Yeah. Any points you want to discuss? Any part of the paper? I think the last unknown
No.
class discussion like brought it home together. It made a lot of sense how it was actually.
Yeah, I think it was a pretty comprehensive discussion.
Okay, then I'll end the stream.